This is the Fields Homework Booklet, question 27. So first of all, stating Newton's law of gravitation, and you are asked to do this in words. If ever that isn't stated, you can use the equation, but do be very, very careful to define all the variables and to make the point that we are referring to point masses. So Newton's law of gravitation says that the attractive force between point masses is proportional to the product of those masses and inversely proportional to the square of their separation. So 3 marks allocated here. The first one for attractive force and point masses, and then these 2 further points follow. Next, you are asked to consider the centripetal force acting on a planet in an orbit and to show that the time period of orbit squared is proportional to the radius cubed. This is the proof of Kepler's law, and you should be very familiar with this. So you are going to be stating that the gravitational force is equal to the centripetal force. So here you're using Newton's law of gravitation, so it follows on nicely from part A of the question, and here you're thinking about a centripetal force and the equation for that. You could use the alternative with angular velocity in it, so m omega squared r, and you'll see in question 23 that I did do it that way on that occasion. So equating the 2 expressions for force and then simplifying and rearranging. You do need to bring in this version, the fact that the velocity equals the circumference divided by the time period. So I've done that here. That leads us to this expression, t squared equals 4 pi squared r cubed divided by gm. Now you have been asked to prove this relationship of proportionality, so you should be stating that the 4 pi squared divided by gm, these are all constants leading to this final conclusion. Do be aware this is a required derivation, so that increases the chances of it appearing on an exam paper fairly frequently. Next, you're told that the Earth's orbit has a radius of this value and that the time period for the Earth's orbit is 365 days. You are then given the radius of the orbit for Mercury and asked for the time period of its orbit. So you should be recognising this as a ratio style question, and I very much hope that you're not starting to use the full equation and put all the constants in. Now it is possible that you're happy to go straight to this point through understanding Kepler's law. So Kepler's law says that the time period squared is proportional to the radius cubed. Now that means that a greater radius would give a greater time period and a smaller radius would give a smaller time period. But you also have to remember the cubed and the squareds. So you might be able to see that the time period for Mercury will depend on the time period for Earth, but we do need to square them both. And then that you would expect to multiply by the ratio of the radius of Mercury to the radius of Earth, and then cube that. Now if you don't see that from the sense and logic of it, then do go back a step and start here, where you know that t squared divided by r cubed is a constant. And then putting in subscripts for your 2 situations, which were Mercury and Earth, and careful rearranging will get you to this point. Also be aware, if you were asked to work out a radius instead of a time period, it would be easier just to turn this upside down so that what you are trying to find ends up on the top of the equation, making everything more straightforward. So that leads you through to an answer of 87.5 days. finally, you're told about another planet. So you're now told that Neptune orbits the Sun once every 165 Earth years. So now a much longer time period being shown. You're asked to calculate the ratio of the distance from the Sun to Neptune to the distance from the Sun to Earth. Please ignore everything in the brackets here. You'll see I haven't read the question and I've gone a little autopilot for a moment, but it's much easier if you read the question and see that you're supposed to find the ratio. So again, I'm starting with my expression from Kepler's law. You may notice I've written it upside down to the last time that I used it up here. Here I had t squared divided by r cubed is a constant. Now I'm saying r cubed divided by t squared is a constant. That's because I know I want to work with the radii, so I just think it's easier to start with Neptune on the top here, and then I know I'm going to be dividing both sides by the radius of the Earth cubed. So careful rearranging leads me to having Neptune on the top and Earth on the bottom, and then I simply need to get the ratio of the time periods, square those and take the cubed root. Okay, so you could just do it as to the power of 2/3, or you could do it as two steps, where you do the squaring of Tn divided by Te and then take the cubed root. And that leads you to an answer of 30.1.